Now, polling can actually have a broader context than that, but yeah, it's an aspect of polling. The idea is that you're continually looking at that device to see if it's available. I think I indicated to you that I had a student one time that decided to try and find out
Well, it shows
how many times it actually went through that loop between the entering of two consecutive characters. And
It shows how many cycles, like right down at the bottom in the simulator, so you can sit there and watch it count to like lots. I saw it and watched it for like
Yeah,
a few
it
minutes.
does. It's just,
That's a lot.
and you think that you're a pretty quick typist, but you're not compared to that kind of system. Now, when you're running a dedicated system where all it has to do is to process your input routine here, it's no big deal because it wouldn't be doing anything else anyway. But when you get into an environment where you do any kind of multitasking, where there are lots of other jobs to be done, this can be kind of annoying. One of the easiest ways to visualize the problem with busy waiting is to think in terms of the time-shared system, which we don't see around that much anymore with the advent of the personal computer and things like that. But I'll show you in a few minutes how it applies here too. But think of this situation where you've got a processor here, and you've got a whole bunch of users out here, and so on, all of which are basically using the same CPU. Now, of course, a processor, a core, if you wish, has only one stream of instructions that it can be executing at any given time. That's just the way they are. I mean, go back and think about the design of this system that we're working with, which is typical von Neumann architecture, where you've got a program counter that's telling you this is the next instruction to be executed. There's no option. It doesn't say, well, you can do this one or you can do this one if you want, you know. It just doesn't work that way. It's very deterministic. So how do we handle systems like this? Well, the idea behind it is this, that we have a list of things that we'll call the ready queue, where we have user 1, user 2, user 3, and here we have a processor over here. It will take this user and load their information into the processor. In doing that, then, each one of these will move up in the queue, up toward the head of the queue. And then depending on how the system is implemented, at some point, user 1 is going to get evicted from the CPU. True time-sharing systems, they will be allowed a certain amount of time, typically on the order of milliseconds, which a thousandth of a second, it seems a really short time, but when you realize how quickly the CPU goes through instructions, you can get a lot done. The other alternative is that it will stay there until the program blocks itself typically for something like an I/O operation or whatever. But at any rate, under some circumstance, that process will leave. If it isn't yet completed, if we haven't hit a halt instruction, it cycles it back through, goes back in at the end of the queue and works its way up and eventually gets another time slice. Now, suppose that user 1 and user 2 are at this point in their programs, but user 3 has some worthwhile work to do, something other than just loading that status register and checking it. Okay, so through 2/3 of the CPU time, we're doing nothing more than loading and branching. Nothing's really being accomplished. 1/3 of the time, after these two have used their time slices, then user 3 comes in, and finally the CPU gets to do something for a little while, drops out, comes back in, picks this up. Again, since we're talking orders of milliseconds, most of us can't type 2 characters in a millionth of a second or a thousandth of a second. So it's probably still going to be sitting there just looping. Okay, so people realize this pretty quickly in time-shared systems that you can end up, in essence, wasting an awful lot of CPU time in doing this kind of an operation. Now, the thing that we use on systems other than this LC3, the LC3 system doesn't do this, but I'll show you how the thing works. We alter this system in this way. We have our CPU over here, of course, and then we have our ready queue. And process comes off of the head of the ready queue into the CPU. Now, when it requests some I/O services, instead of sitting here and waiting for that I/O event to occur and then pushing it back into here, if you have an I/O request, it bumps you up here into a suspended state. Otherwise, when it finishes, as long as it's doing the productive work, like when the time is up, it goes back into the ready queue. Now, the mechanism that is used for this thing is called an interrupt. If you think about this process for a moment, you'll see that now the operating system, the thing that's actually running the CPU, has a lot of things to keep track of. One of them is it has to keep track of all of these users and their programs and where they are and what's happening. This change through here is called a context switch. There's a lot of work that goes on. You'll encounter that when you take the operating systems class. To do a context switch, remember all these registers that you use? There's only one set of them. And so if your program is going to use the registers and somebody else's program is using the registers, it has to save all those registers. It has to save a copy of the program counter so that when your program comes back in, it knows where to pick it up. disciplines. You don't start over again from scratch every time. Okay, so all that information storage and handling of all of that is called context switch. When you make an I/O request and your program gets suspended, there's some information that is kept there relating to what's happening with your program. Part of it is, of course, just like this context switch, it saves a complete context. So that when your program comes back into the CPU, it will look to that program as though nothing has changed. The CPU, all the registers, all the memory, all the rest of that is just like it was when you stopped. That's an important thing. Now, the other thing that you have to keep track of is what I/O device are you waiting on? You have to know that. That's a part of the way the thing works. So that when you make the I/O request, it comes through here. You get suspended. When the I/O is complete, it'll put you back in the ready queue. So that all the time that you're waiting for that I/O, you're not competing with these other people for the resources of the system. It frees the system up. So again, if we've got both of these users here waiting on I/O, and instead of just spinning that CPU around in a wait loop, they go off someplace else, and if user 3 is the only other user on the system, he has full access and just keeps getting good work done until such time as somebody's I/O completes, and then they get put back into the ready queue and off we go. Now, there are two items that we have to think about if we're going to use this kind of a system. First is that we have to enable the interrupt system in the first place. You remember, since we're talking about the keyboard, we'll go ahead with the keyboard status register. Bit 15 out here at the end was used as a ready bit, and just kind of grayed out all the rest of that 16-bit word, and didn't worry too much about it. Now we'll say that typically the next bit down doesn't have to be. When you get away from that bit 15, one bit is just as easy to work with as another one. But very often, why it's bit 14 is what we call an interrupt enable bit. One says that interrupt accepted. 0 says no interrupts. So you see what can happen here with a program as it is suspended. What the operating system looks at is, as they point out in the book, you just take an AND of these things, and when you get a 1 signal out of this thing, you get what we might call a wake up, which will wake up that process that's in a sleeping state and put it back into the ready state, ready to be executed. So typically, this is the way modern systems work. As you begin to run a program, you either set or clear this depending on whether or not you want interrupts enabled. If you do, then it will work in pretty much this manner. Now, that's the basic idea of the interrupt. The problem is, do you really want that I/O system to be able to stop any other program that's running, be able to move you? So we get into another business, and that's priority. Most all computer systems anymore contain within the CPU here a thing called the process status word, PSW of course, which contains a lot of information about what's actually going on. But one of the important things is that depending on the design of your system and how many levels you want, there are a certain number of bits in there that define the priority of the operation that is currently being performed. For example, if you get to the point where you're doing a context switch, changing from one task to another task, that's pretty high priority. You don't want that thing interrupted in the middle of that switch where you have saved half the registers but not the other half. You don't want that kind of thing happening. So context switches run at a pretty high priority. User processes are typically low to moderate priority. Interrupt service routines are a little bit higher. So that if a process is in here doing some arithmetic and working with things, and the keyboard says, I've got that character, it will interrupt that program and put this suspended program back in the ready queue, and then let this one go on and finish until it gets there. So someplace down in here, there are some bits that define the priority of this device. So each device has a priority, each user has a priority, each task that the processor is working on has a priority. If the device priority is higher than the priority of the current process in there, which is contained in the process status word, it will interrupt that process, complete the I/O transfer, and then return to what it was doing. If the process that's currently running in the CPU has higher priority, then the I/O device will wait a while. And that's one of the ways in which we increase the efficiency of the CPU system. Keep it working on productive parts of the process. Now, like I say, looking at this thing from the point of view of a time-shared system where you've got a lot of different processes there actually running, you think that may not be the same as a PC, but it is. There are a lot of processes that tend to run in the background on your PC while you're working. look at a priority list, your program might sit right in here. Okay, somebody, can you think of any other processes that are running most of the time in the background on your system?
Display.
The what?
Display.
You're continually refreshing your display. That runs pretty close to what you're doing because it's part of your communication system. You got a clock on there anywhere that tells you what time it is?
Yeah.
That's probably pretty low priority, but it's down there. Now, I don't mean the system clock that's telling you, when to move on to the next instruction and things like that. I mean that little thing down there at the bottom that says it's 10:30 a.m. Okay, any other kinds of things like that you have running in the background?
Antivirus.
What?
Antivirus.
Perhaps. And you can actually maybe even have some malware running there in the background that you're not aware of. Yeah. There are a lot of things that actually go on within that processor that you may or may not be aware of. A lot of people will stream music, background music through the computer at the same time that they're working on writing code and so on. See, there are just lots of different kinds of things that can and do go on in there. So, and all of these things run at different priority levels. One program can interrupt something at a lower priority, but not one at a higher priority. But the whole purpose here, you end up with I/O devices typically being at a little higher priority than the user program. Again, none of this is hard-coded. It's usually things that, well, in the case of PCs, they're usually put in as part of the way a particular operating system works. In bigger systems, why they're set by the system manager. Ways to tune the performance of a big system. Okay, so if you want to look at kind of a sequence of events here.
I have a quick question.
Yeah.
What would be at the very top? of
The
that
operating system.
The priority system.
The operating system.
The operating system itself.
Yeah.
Where does control alt delete fall on that? Would that be I/O device?
That's actually a request to the operating system.
Because that has a pretty high interrupt, doesn't it?
Yeah. Yeah. That should interrupt just about everything. Yeah. We have a program running here, and the general sequence of thing kind of goes like this. We're executing some instruction here. And n plus 1 and n plus 2, n plus 3, we're just gradually working down through the program. Then if you get an interrupt, Now, remember, this sequence of actually executing an instruction. Fetch, decode, find your operand addresses, you fetch the operands, you execute and store results. Now, what if this interrupt signal comes when you're right here? Let's say, for example, well, the systems are all set up so that if that signal comes partway through the execution of a machine instruction, you will actually, first of all, complete the current instruction. Now that's really significant. You have to be able to finish whatever instruction you're in the middle of. Then you service the interrupt, and these things are typically referred to as interrupt service routines. It may take several cycles to do that. Several cycles. It actually goes through a complete context switch. Because the interrupt service routines, just like any program, are going to be working with the registers, with the program counter, all the rest of that. They're just programs. It's really all they are. And so it has to save all the information about the program that it's running. Then it has to load and execute the program that actually services that interrupt. When it gets to the end of it, it does another context switch, comes back, returns to your program, and it just picks up right where it left off, hopefully n+4, and so on. And it's the context switch that allows it to actually do that. It saves the program counter so that it knows right where it was in your program. It saves the registers so that the registers are all the same. You save the system state. Everything that reflects exactly where the system was when the interrupt occurred. And when you do the context switch at the end, it restores it. Gets us right back where we were. Okay, that's the basic idea of how the interrupt works. Now, the LC3, as it is set up, doesn't really work with the interrupt-driven I/O, but this is the idea of how it works. I encourage you to read carefully this blue box, 8.1, example 8.1 in the book. He goes through a numeric example of how interrupt-driven I/O actually ends up saving time on the computer. The idea is sort of like the diagram that I had up here with several users, some of which are just spinning their wheels in a busy wait loop. But that's really what it talks about, but he does it pretty precisely in terms of the specific numbers.
Does it use more power in addition to more time?
No.
Or not the interrupt, but the polling?
No, because ultimately, if you think about it, the processor and all the rest of it are just electrical circuits. They've got to be doing something. There has to be current and voltages in that system all the time, whenever it's turned on. So when you're loading registers and changing the values in them and all the rest of that, that doesn't really increase the amount of power that's being drawn, because those devices are in use anyway.
Then how come when you're using high resource-heavy programs, your computer gets a lot hotter?
Typically that comes from the communications with the devices and the things that are involved there. Because the CPU is actually changing its state every tick of its internal clock, whether there's anything going on or not. Okay, a lot of the, for example, if you're doing a lot of memory-intensive work, you're doing a lot of stuff with the communications lines, things like that, and it does tend to heat things up. But if you just look at the processor and what's going on within there, it doesn't really change. Now, let's talk about one other thing. On this assignment, I told you not to use these. You remember we talked about track 25, which is a halt routine. There are two others that
I'm supposed to use this.
we can work with. 21, I'm pretty sure it's 21, but let's, is a routine here we go. 21 is out. And you can use this out just as an instruction in the program, just like you would insert halt. You can do halt or you can do track X25. They mean the same thing. You can do the same thing with out. What out does is it prints the contents of register 0, bits 0 through 7, as an ASCII character on the display. Now this runs basically as an interrupt. It's kind of what it's doing. Because if you watch what happens if you step through the program and watch what happens to the program counter and even the instructions being displayed on the screen as you go through it. Remember where it left things if you executed a halt? You were down in some odd part of memory with an odd address and instructions that you know you didn't write and they don't have anything to do with your program. What you're seeing there are the interrupt service routines. Okay, that halt instruction is actually a relatively high priority interrupt service routine. Out is a similar kind of thing. There is code out there that will handle your output for you. Does a lot of the stuff that we've been hand coding. It does one character at a time. Whatever you have in the low order 8 bits of register 0. Okay, that's where it has to be. That's where the interrupt service routine is looking for. You can't say out register 1 and expect to print a character from register 1. Won't do it. Because the routine is hard-coded to reference register 0.
So it'll only do 8 bits then? And so you would
All
have
of
to.
the ASCII codes are 8 bits, yeah.
Oh, okay, never mind.
Yeah.
I see what you're
Now, there is an extension of the ASCII codes that talk about, that goes to 16-bit ASCII, but this system only works with 8 bits, yeah. Anything that's in the high order 8 bits of that register is just ignored. Just doesn't do anything with it.
Which was on the test, right?
Yeah. So if you have a character in the high order and a character in the low order 8 bits, the only one that's going to be printed is the low order. Now, similarly, 23, yeah. In reads, well, it actually does more than just read the character. And I've been trying to remember what the prompt is that it prints, and I don't recall. Might be a question mark, it might be a greater than symbol, or who knows what. Then reads a single character puts the ASCII code in same place, register 0, bits 0 through 7. Just as a high order byte of register 0 is clear. Anything that you may have had in there before will disappear coming out of this routine. In other words, the only thing that will be in register 0 at the conclusion of the execution of an end is the character that the ASCII code corresponding to the key that you pressed goes into register 0. Okay, this is the basic I/O assistance that this system gives you. Notice that it does not really give you the capability of typing in a whole character string. It's one character at a time. And so that can kind of make some kinds of input a little bit difficult to work with.
What kinds of input are you thinking?
Pardon?
What types of input are you, would be difficult.
Well, if you want to, as in the case of the assignment there, type in an integer, 3 or 4 digit integer. If you're using this thing, you're going to do 1 digit, another digit on the next line, and another digit on the line after that. I mean, you can make it work, but it's not quite the same kind of thing. Okay, well, we're out of time. We'll write some code next time using these kinds of things.